So you've built this incredible AI model. It's looking great. But how do you know, really know, that it's going to work out there in the real world when it actually counts? Well, that's the big question we're tackling today: how we can build an AI that we can actually trust.
Let's be real. Is your AI a legit genius that can handle new situations it's never seen before? Or is it just a really, really good guesser that basically memorized the answers to the practice test? The answer to that question is everything. It's the difference between a game-changing tool and a flat-out dangerous liability. And this slide just lays it all out, right? This is a trap so many people fall into. On the data it was trained with, the model looks like an absolute rock star. We're talking 99% accuracy. But then you set it loose, and in the real world, its performance just tanks. This gap, this is the silent killer of so many AI projects. So this huge, dangerous gap between how it does in practice versus in reality, it's a classic problem, and it's got a name. It's called the overfitting trap. Okay, the best way to think about this is like a student cramming for an exam. They haven't actually learned the material. Nope, they've just memorized the exact answers on the practice sheet. So when the real exam has questions that are just a little bit different, they're toast. That's overfitting. The model memorized the noise, not the signal. Okay, so the first logical thought to fix this is to come up with a better test. And that brings us to the most common starting point for a lot of folks. A simple method that seems to make sense, but as we're about to see, it's got a huge flaw. It's super intuitive. Here's the breakdown. You take your data and split it in two. The big chunk becomes your training set. Think of it as the textbook, all the homework problems, everything the model gets to study. And then you've got this smaller chunk, the test set. This is the final exam, kept under lock and key. The model has never seen it before. Simple enough, right? But here's the giant, glaring problem with that approach. Your final grade, your model's performance, it can be wildly different depending on which specific examples just happen to land in that one test set. What if, just by pure chance, all the easy questions ended up on the final exam? You'd think you have a genius model, but you just got lucky. Yeah, basically, this whole thing comes down to luck. And let's be real, when we're building AI for things like medicine or finance, luck is not a strategy we want to bet on. So, how do we take luck completely out of the picture? Well, this is where a much smarter, much more robust technique swoops in to save the day. Meet cross-validation. Think back to our student. Instead of one single high-stakes final exam, what if we gave them, say, 5 different exams, each one covering a slightly different slice of the material? We get a way better idea of what they actually know, wouldn't we? Well, that is precisely the idea behind cross-validation. It's like a system for giving our model a whole series of exams. So let's dive in and see how this clever idea actually works. The most common way to do this is called K-fold cross-validation. First, you chop up your data into K equal size pieces. We call these folds. 5 is a really common number, so let's stick with that. Then the magic happens. We're going to run a process 5 times. In each round, one fold becomes the test, the exam, while the other 4 are used for training. And you just keep doing that, rotating which fold is the test until every single one has had its turn. And at the very end, you just average all the scores together. So this is what step 1 looks like visually. We take our whole pile of data and just slice it into 5 equal chunks. Fold 1, fold 2, and so on. Easy enough. Now the fun begins. All right, round 1. We're going to hold back fold 1. That's our test set. The model gets to train on everything else, folds 2, 3, 4, and 5. Then we test it on fold 1 and write down the score. Next up, round 2. We just rotate. Now fold 2 is the test set. The model trains on folds 1, 3, 4, and 5, and boom, we get another score. You can probably see where this is going, right? In round 3, fold 3 is the test set. And we keep going like this until every single fold has had a chance to be the test set, just once. The beauty of this is that no data gets left behind. Every single data point gets used for both training and testing. There's no more depending on one lucky final exam. And this is where it all comes together. Check out these results. Just look at the scores we got on each run. One time we got 92%, then 88%. Another time we got a whopping 94%. Now think about it. If we had only done that simple train/test split, we could have gotten any of those scores just by pure luck. Talk about unreliable. But by averaging all 5, we get a final score of 90.8%. That number, that is an estimate we could actually trust. Okay, so let's tie this all together. We've gone through the how, but the why is what's really important here. And it all boils down to a single crucial word: trust.
So, what's the big takeaway? The power of cross validation is huge. First, it gives you a performance number you can actually believe in, because it smooths out all that randomness from a single lucky or unlucky split. Second, it's super efficient with your data. Every single piece of information gets used to both teach the model and to test it. And what does all that lead to? The most important thing of all: genuine confidence that your AI is ready for the real world.
So there you have it. That's cross-validation in a nutshell. It's not just a fancy technique. It's a fundamental shift from just guessing to actually knowing how well your model works. Which brings us to one final big question for you. Now that you know how to build and test an AI you can truly trust, what big problem are you going to go out and solve?